Hey, over to you, John.
All right. So like Joanna said, if anybody has any questions, feel free to shout whenever. Otherwise, I'll assume everyone is happy. So thanks for joining this tech forum today. We're going to talk about granule protection tables in TFA, which is a new addition as a part of supporting RMV9 realm management extension. We're going to cover a few different topics about that, including what granule protection tables are, how they work, how to configure them, and how they are dealt with in trusted firmware. Start off, the ARM architecture we all know has two security states, secure and non-secure. Realm management extension changes this and adds two more called root and realm. We're mainly concerned with root right now, which is essentially just EL3 and where trusted firmware lives. With these new states comes a new way of controlling and restricting memory accesses between the states, and that is where the granule protection tables come in. They define which physical address spaces can be accessed by each security state. Protected memory is tagged with one of 6 possible GPI values, which stands for granule protection information. If you look at the table on the right, the security states are listed along the top and the different GPI values are down the side. For the most part, access permissions are pretty intuitive. Memory marked no access can't be accessed from anywhere. Marked any can be accessed from anywhere. Root can access everything, and realm and secure can both access their own memory in addition to non-secure memory. Non-secure code is confined to non-secure space only. If the granule protection checks are enabled and the program attempts to access memory outside of what the GPTs allow, it triggers a granule protection fault, which can then be handled by the system as it sees fit. So now that we've covered what the GPTs are, let's talk a little bit about how they work. The tables can use either a 1 or 2 stage lookup process, dubbed level 0 and level 1, or L0 and L1, as I'll refer to them for the rest of this presentation. Each entry in an L0 table controls a relatively large amount of memory space, and we'll talk about exactly how much in a few minutes. An entry in the L0 table, called an L0 descriptor, can either map its entire space to a single GPI using a block descriptor, or contain a pointer to a level 1 table using a table descriptor. This allows for much finer delegation of the same memory space by dividing it into much smaller chunks called granules, hence the name granule protection tables, at the expense of requiring more table memory and an additional lookup step for each memory access. As seen in the diagram on the right, block descriptors are a single step lookup using only the L0 table. You can see these in the green boxes and arrows. These tables are typically placed in SRAM for the best possible access time and security. Block descriptors are fixed after initialization, meaning that the GPI value cannot be changed once the tables are configured. L0 table descriptors use a 2-step lookup process as opposed to 1, and they link to an L1 table shown in orange, which contains an array of granule descriptors. Granule descriptors contain 4-bit GPI values corresponding to individual granules within the L0 region, and the GPI values here can be changed at runtime using SMC calls in the granule transition service, which we'll cover in a few minutes. If you're a little
Sorry, I have a question. Sorry to interrupt.
Yeah,
Sorry.
no
the second bullet and fourth bullet seem conflicting. Sorry, what is? I guess I don't quite grok the difference between the two. What does it mean? It's fixed after initialization, but you can change it later with SMC.
That's kind of a typo on the slide that you pointed out. The GPI is only fixed for block descriptors. For table descriptors, you can change the GPIs at runtime.
Well, so is the GPI changing the type for the next level table, or is it changing it for the memory pointed to by the next level table?
It's changing to the memory pointed to. So a block descriptor, which is just a single step lookup, the GPI in that block descriptor describes the entire memory region.
Mm-hmm.
Does that make sense?
And the table descriptor, and the table descriptor is sort of an override of the L1 table. L1 table descriptor in terms of GPI?
So a table descriptor points to an L1 table, which then that L1 table controls the memory as opposed to the L0 table.
Okay, all right, thanks.
Right. I have a sample of a lookup in another slide or two that I think will help clarify that. So if not, let me know and I'll go into that a little bit more.
Okay, thanks.
So before we do that, let's talk about how these tables are configured. there are three main parameters that define how the tables are organized: the PPS, PGS, and L0 GPC size. PPS stands for protected physical address size and simply defines the total amount of protected memory. It is configurable from 4 gigabytes up to 4 petabytes and is passed into the GPT library API when first setting up the tables. PGS stands for physical granule size. This defines the size of each granule, which is the smallest individually assignable piece of memory. This value can set from 4 kilobytes to 64 kilobytes and is also passed into the API at table creation. Lastly, the L0 GPT size determines how large each level 0 region is. This value is fixed in hardware to one of 4 possible settings from 1 gigabyte up to 512 gigabytes and can be read from the GPCCR EL3 register. These parameters all interact. The total number of L0 descriptors is the PPS divided by the L0 GPT size. The number of descriptors in each L1 table can be determined in a similar way by dividing the L0 GPT size by the PGS, and then dividing again by 16 since each descriptor contains 16 4-bit GPI values. And by GPI values, I mean the values that assign the memory type of each granule. Anyways, here is a fairly simple example. This is a completely unrealistic memory layout. It's only 16 bytes for the PPS with a PGS of 1 byte and a 4 byte L0 GPT size. You can see over on the right, the L0 regions are marked in green, and then in orange, you can see the individual granules. So let's assume we want to access physical address 0xD, which is in binary 1101. We figure out which L0 entry we want to look at by looking at bits 3 and 2 of the physical address, which are 1, 1, so index 3, which you can see highlighted in red. We can see that that's a table descriptor, so we will now look at bit 1 of the physical address to figure out which granule descriptor within that table descriptor we want to use, which is 0. And then in this example, each granule descriptor contains 2 GPI values, so we look at the bottom bit for that, which is a 1. So that points us to the second entry in that L0 region. Does that, and in fact, I'm hoping that kind of explains everything a little bit better than the previous slides did.
Yes, at least for me it did. So yeah, top 2 bits is because L0 GPT size is 4 bytes. And the third bit is because your example says that L1 table has 2 entries as opposed to, I don't know, the real architecture having 4 values, 4-bit values.
Yeah, the real architecture of granule descriptor is 64 bits, so you have 16 total GPIs, but in this small example, it's just 1 byte each, so you only have 2. So in a real system, you would have the index bits would be much larger, but otherwise it's essentially representative.
Okay, thanks.
All right, next slide. So anyways, now we'll talk about how this pertains to trusted firmware. In the reference implementation on FPP platforms, we initialize the tables in BL2 on the primary CPU. The first step of that process is turning on the MMU. This is done to simplify cache management operations and simplify cache management because everything needs to be fully coherent across all cores as they're brought up. Once the MMU is enabled, all the L0 descriptors covering the entire protected space are initialized to GPI any using the API GPT init L0 tables. The desired PPS value is supplied here along with the base address for the L0 tables, which, like I mentioned, would typically be somewhere in SRAM. Once that is complete, the system can go and discover initialized DRAM before the next stage of initialization, where the desired protected regions are carved out of the space we previously initialized. In this function called GPT init pass L1 tables, the PGS is supplied along with the addresses of the L1 table and an array containing information about desired protected memory regions. In this array, I mean, I don't really want to go into a whole lot of detail, but basically you define what memory regions are allocated to what GPI and whether you want to use block or table descriptors. This function can be called multiple times in case you want to place the L1 tables in different locations, such as if you have multiple banks of DDR, which each might have their own tables.
So question, sorry, on the previous slide. So you say L0 is placed in SRAM. Does the SRAM itself not have a GPI value?
So
Is
yes.
this so? Like you're assuming that SRAM is automatically locked to root realm, right? And nobody else can, no other realm can access it.
So
Not
you would
realm.
want to make sure that SRAM is allocated to root, and anywhere that contains your tables would be root.
Correct, but so it seems like you turn on the MMU first, and then you set up the GPT. So yeah, so it seems like there's an assumption that by default everything is root. I guess that is the architecture. I don't know.
So by default, everything is configured to, or by default, granule protection checks are not enabled. So anything can access more or less anywhere.
Oh, I see.
So until
okay.
we turn on the checks, it doesn't really matter what's in the tables. But once you turn on the checks, you would definitely want to make sure that your tables are in GPI root. Otherwise, someone else could go modify them.
Okay, makes sense. So essentially, you will have this L1 table that points back to this SRAM that marks it as GPI root. There will be some entry for that.
Yes, exactly.
Okay.
John, just to clarify on that, I think we create L1 tables only for the DDR range, right? We don't create it for the actual SRAM, do we?
I think we did have the SRAM defined as a granule regions or table descriptors. I can look again. Maybe you're right, but I'm pretty sure it was a granule.
Yeah, I think it's not needed because SRAM by default is a root only region. It would have peripheral side filters, which means that any other address space code or data cannot be accessed if it's in SRAM. So typically what we do is only the DDR regions which can be dynamically allocated to pass are described in the L1 tables. And this is what gets protected through the GPC checks. All the fixed peripherals like SRAM, secure DRAM, any other secure peripherals or any root peripherals will have peripheral side filters. So it's protected irrespective of the GPT from reset.
I know we had regions defined for those in our reference code.
Okay, so you could describe it in the GPT tables as well, but since they have peripheral side filters anyway, it shouldn't make a difference over there. It's mainly yeah.
Sorry, finish your thought. Sorry, Sobi.
Yeah, I just wanted to say it's basically the DDR that's described in the L1 tables. Yeah, we don't need to describe any other region in the.
Okay, that's good to know.
So two follow-up questions, right? Sorry. So the statement that was made is FVP specific, right? So in theory, there's nothing in the architecture that says I cannot include SRAM or peripherals in the GPT, right? I could build an SoC without peripheral side filtering and just use GPT.
Yes, there are some caveats for GPC protection, as in GPC doesn't prevent speculation from another address space from happening. That's what I understand. It's only the actual fetches. So if the truly correct way to do this is you have peripheral side filters, peripheral side filters to prevent other physical address spaces from accessing it. You could configure it in GPT, but then, yeah, that may not add any further protection to the peripheral side filters.
Correct. Yeah. Okay. That makes sense to me. So really the difference is in, it seems like I have to read the spec, but it seems like you can speculate into any of these GPI regions or anything protected by GPC.
Yeah, there are some corner cases with respect to speculation where some speculative accesses are allowed to go through, but yeah, I'm not sure on the details. Yeah. That's
Okay,
what I
thank you.
understand. Yeah.
So a quick question. On a platform that uses GPT, is there a role for a TZC controller, or we just don't need any TZC controller on a platform like this?
Right. So TZZ controller is the traditional trust zone controller that we have on a two-world system. So you can only describe non-secure and secure world protection using a TZZ controller. Now Newmore introduces 4 worlds, which means that TZZ controller effectively has to divide the 4 worlds into 2 worlds. So what that essentially means is root and TZZ cannot differentiate between root and secure. Similarly, it cannot differentiate between non-secure and realm. So it would treat realm and non-secure as belonging to non-secure, and it would treat root and secure as belonging to secure. So essentially, the root world cannot be protected from secure world. Similarly, realm world cannot be protected from the non-secure world if you just have TZZ controller. Now on the FAP, we do have TZZ controller which needs to be configured before we can start running software. But we do a workaround where we mark both root and secure as secure world, and then mark realm and non-secure as secure in the TZZ, and then add GPT on top of it. But ideally, I think in a realistic system, TZZ controller may not make sense in a Newmore system. Yeah, in a CCS system. Yeah.
So if we don't have a TZC controller, and for let's say we would like to have secure partitions running in the secure world. So the secure memory carve-outs, is there any way we can dynamically request for a GPT region to be created for those carve-outs?
So you would create the secure world carve-outs using GPT. And you could make use of Granule transition service to expand or do dynamic carve-outs if needed.
So the Granule transition service allows you to transition non-secure granules to either secure or realm when needed at runtime.
Yeah.
Okay.
So in the TFA implementation, the Granule transition service is currently restricted to realm side currently. Yeah, perhaps in future, once we understand the secure side implications, it can be extended as part of dynamic trust zone use cases.
I thought we allowed secure transitions also, or from non-secure to secure and back.
Yeah, the code is there, although it's only getting invoked from the RMM dispatcher.
Yeah, we don't think we actually don't use it yet, but
Yeah,
it is
yeah.
there.
Yeah, the code is there. Yeah.
Okay. Thanks for all the clarification, Sobi. I probably would not have known those answers.
No worries.
All right, let's go to if there's no more questions, we'll keep moving to the next slide. So moving on. Once the tables have been created, Granule protection checks are enabled using the GPT enable, which is the final step of the BL2 initialization. From here, we move on to runtime firmware in BL3.1, which, if the Granule transition service is needed, we will use GPT runtime init, which will lock the tables and find the parameters of tables for the runtime service. On warm boots, it's a lot simpler, as BL3.1 simply needs to call GPT enable after enabling the MMU, and then it will just reconfigure the registers on that core using the existing data structures.
So, sorry, sorry, I didn't follow the difference between the runtime init and the first init. Well, sorry, what's the difference?
So the first initialization process just sets up the tables in memory. Then when you move to the next bootloader stage, which is BL3.1, which sets up the runtime firmware, it needs to recreate the data structures for itself so it knows where to find the tables and what parameters to use. So since the register addresses have already been set up in BL2, it just has to go read those registers and then walk the tables to find the parameters.
What parameters are these?
PPS, VGS, and L0 GPT size.
Oh, and then it can add entries to, and then it can add or remove entries from the GPT.
You're not necessarily adding or removing, but it can transition GPIs in table descriptors.
Oh, I see. Okay, thanks.
So the runtime service allows granules to be transitioned between secure and non-secure, and then realm and non-secure. But it needs to know where the tables are before it can do that.
Thanks.
So I think there is a correction in the timeline. I think the GPT runtime init should come after enter BL31. It should be one of the orange blobs over there.
Oh no, you're right. That's a typo.
Right. So essentially,
yeah, that's where you're right. That's where.
So essentially, BL2 comes along and it creates the table in memory, and it sets up the carve-outs required for realm world, secure world, and root world. Now BL31 needs to know the location of L0 and L0 table so that it can do a software walk of the table and do a transition according to the Granule transition service request. So it needs to discover that the already configured sysreg, and that's what the GPT runtime init is meant to do. It would read the sysreg, already configured sysreg, and it would enable the software data structures to enable a software walk of the GPT tables at runtime.
Thanks.
Yeah, basically the GPT runtime init and enable function should be flipped in the timeline. But anyways, about the Granule transition service, as mentioned earlier, memory regions configured as table descriptors can have their granules transition between different GPIs and software by using SMC calls. Secure software can request non-secure granules to be transitioned to secure, and then it can send them back. And similarly, realm software can request non-secure granules to be transitioned to realm and then send them back. Root and non-secure software cannot request transitions at all. When a request is received, the GTSI or Granule Transition Service walks the tables to find the granule in question, validates the request to make sure that it's not illegal, then performs the transition. A lock is used to ensure that separate cores don't try to modify L1 descriptors at the same time. And like I mentioned earlier, if the Granule Transition Service is not needed, then there is no need for GPT runtime in it.
So question, right? So the last bullet says non-secure and root firmware cannot request it. I mean, root firmware can, I'm not sure I understand what it means by cannot request, right? Root firmware owns the GPT. If it wants to, it can change it, right? So there's really not a architectural limitation, but a convention in firmware.
Yes, this is a firmware limitation. Because then we've just decided that root isn't, or I mean, you could change the firmware to change it if needed, but in the reference firmware, we've decided that there's no reason for root to be able to change anything at runtime.
Right. Yeah. I was just thinking from an attack perspective. If root firmware is exploited, yeah, it could do anything to the GPTs, right?
Yeah. Yeah. It's okay. Not a firmware limitation. So anyways, at this point, I'm almost at the end. There's a couple of things we still want to update in the future. Right now, the transition service can only transition one granule at a time. So we'd like to expand this to be able to transition a range of granules instead of making multiple calls. And it also relies on a single global lock for all L1 tables. So we could improve performance by having multiple locks across separate L1 tables, or even locks for each L1 descriptor. And then at some point, we'd like to add support for contiguous descriptors, which essentially allow a single L1 descriptor to define a memory region that's larger than a granule, but still smaller than the L0 GPT size to allow improved performance and better cache hit rates and less fetches and that sort of thing. But that's about all I have. If anyone has any more questions, then we can talk about that now.
Sorry, last bullet of the last slide. Can you expand on that a little further? So how would you, I'm not sure I understood what you meant by you can use one entry to, did you say you can use one entry to describe multiple granules?
So a contiguous descriptor is a So L1 tables would usually have granule descriptors, which describe each granule individually. A contiguous descriptor allows you to describe a large range of granules from several megabytes up to several hundred megabytes. I think it's 2 megabytes at the smallest and 512 at the largest. I'd have to look that up to confirm, but so you essentially have a contiguous descriptor in one of your L1 regions that says how big this is, and then then the size of the contiguous descriptor causes that area to be I'm trying to think of what the best way to describe it is. It's if you have
I mean, is it you set a few bits and tell it, okay, the next few granules belong to this this particular entry, and they all are, I don't know, a particular GPI?
Sort of. So you would set all of the, I believe all of the GPIs that would fall within the contiguous descriptor need to be the same. So all of your granule descriptors need to match, but then you have one contiguous descriptor that says all of these are a part of a 2 megabyte region. And then whatever region that happens to fall in, aligned to 2 megabytes, would be the contiguous region. Is that correct, Sobi?
So effectively, yeah, you have, if you have a 2 MB block of similar or same GPIs and you mark them all as contiguous, it means the CPU can optimize the TLB entries for that contiguous entries. So instead of having a per page TLB entry, it could choose to have just one entry for a 2 MB block, which allows to have more optimal TLB utilization, and it's yeah, basically it enhances the performance when TLB is flushed and invalidated. So yeah, that's the idea. It's similar to the translation table contiguous descriptor. I think that the theory is the same. Yeah.
Okay, thanks.
Well, that's about all I have. So if there's no further questions, we can wrap it up.
Thanks, John. Yes, I got nothing else for the agenda today. It was just this session. If there's nothing else, we can get I guess, 30 minutes back of our day.
All right. Thanks, everyone.
All right, thank you. The slides and everything will be updated. So John, I guess you can send me. I think you saw a couple of edits you probably want to do. If you,
yeah, I'll fix a few things and send them on over.
Yeah, and then people listening to this recording can go and look at the PDF version and get the correct slides. All right, brilliant. All right, thank you, everybody.
Thanks. Bye.
Thanks. Bye.